Hello. I'd like to do this third question on optimization. It's the one that I did not get to in any of the classes, and so I'd like to give you an example of a solution. So a company is designing propane tanks that are cylindrical with hemispherical ends. Assume that the company wants tanks that will hold 1,000 cubic feet of gas, and that the ends are the most expensive to make, costing $5 per square foot, while the cylindrical barrel between the ends costs $2 per square foot. Use calculus to determine the minimum cost to construct such a tank. Okay, so here's our barrel. Excuse my drawing skills, but we would like to think about the volume. So here's going to be H. That's going to be the height or the length of the barrel. And then the radius is the radius of that cylinder. It's also the radius of the sphere, the hemispheres. So total, we have two hemispheres. So we have a whole sphere and we have a cylinder. So our volume is the volume of the cylindrical barrel part plus the volume of a sphere. And we know that we want that to be 1,000 cubic feet. Okay, that's going to be our constraint. We know that no matter what, our propane tank is going to hold 1,000 cubic feet. So once we know H, we could determine R, or once we know R, we could determine H just based on the fact of what we want the volume to be. The thing that we're trying to minimize is the cost. So our objective function needs to be a formula for the cost. So in order to figure out the cost, we need the surface area of each piece because we know that the cost is based on which piece it's on. So the surface area of the barrel is 2 pi RH. Okay, this is from a formula for the surface area of a cylinder. Okay, we find the formula for the surface area of the cylinder and we don't include those two ends. Okay, and the surface area of the caps is the surface area of a sphere, which is 4 pi r squared. These are formulas you can look up. Of course, on an exam, I would give you these formulas, but for these purposes, you could look them up because they're a homework question or an in-class question. So the cost of each type of metal is going to be $2 per square foot for the barrel and $5 per square foot for the caps. So total, for our objective function, which is the total cost, we're going to get 4 pi RH plus 20 pi r squared. We have a constraint, and that is our volume. Okay, so we're going to put these two together to get an objective function in just one variable. I'm going to take that volume equation and solve for one of the variables. H really looks like the easier one to solve for, so that's what we're going to do. So our objective function is 4 pi r times 1,000 over pi r squared minus 4/3 r. That's what we get when we solve for H, plus 20 pi r squared. And our domain here goes from, I went too far, goes from 0 to, I'm not really concerned about where it goes to, but I know that the radius can't be 0 or else we'd have no propane tank, there'd be no volume. So we can't include 0, which automatically tells me we can't use the extreme value theorem because the extreme value theorem is only valid on a closed and bounded interval. That means the endpoints have to be included. So we're going to have to use the first or second derivative tests. Okay, so that's how we're going to proceed. So we're going to take the derivative of our objective function. So remember, I'm going to rewrite our objective function so it looks a little bit nicer. Now I'm going to take the derivative, negative 4,000 over r squared minus 32 pi thirds r plus 40 pi r. And then I'm going to take this derivative and I'm going to use it to find the critical values. Okay, so just rewriting the derivative, thinking about the critical values, they occur when the derivative is 0 or when the derivative doesn't exist. This derivative does not exist when r is 0. Of course, 0 is already not in our domain, so that's not a new critical value. So now we need to find where it equals 0. So just simplifying that left-hand side of the equation a little bit, combining the second term and third term, we get 88/3 pi r. Okay, and now we solve. I'm going to move negative 4,000 over r squared to the other side. We're going to multiply both sides by r cubed and divide by 88/3 pi on both sides. We get r cubed equals 3,000 divided by 22 pi. So r is the cube root of 3,000 over 22 pi. This is approximately 3.514 if you're interested, but the exact value is this cube root right here. So now we're using our first derivative test or our second derivative test. Let's go ahead and use the first derivative test. So we're going to find a value to the left of the cube root of 3,000 divided by 22 pi. Let's try r equals 1. We put that into the first derivative, which is right here. Input that into the first derivative. When you input 1, we get negative 4,000 plus 88/3 pi. Okay, that's going to be a negative number. Okay, so we add that to our first derivative chart. All right, so now let's choose a number to the right of our critical value. Let's try 10. Okay, we input 10 into the first derivative. Here's our first derivative. Input 10. What are we going to get? Negative 40. So negative 40 plus 880 pi over 3. It's a little bit more than 880. So negative 40 plus something a little bit bigger than 880, that's going to be a big positive number. And so we get a positive first derivative. So here we have a first derivative that's negative, then it changes to positive, and that's all it does. We know that function only decreases and then starts increasing. That means right here we have a local minimum. And since it's the only critical value and that function never decreases again, it's also a global minimum. Let's go back to the question and see what the question asks us. It says, use calculus to determine the minimum cost to construct such a tank. So our answer should be the minimum cost. So let's go back and calculate that. So we need to take that critical value, input it into our objective function right here. Okay, and then we get the maximum cost, the minimum cost is approximately $1,707.27. Okay, and that's our answer. That should be a reasonable estimate. Okay, make sure that that sounds like a reasonable estimate to you. All right, the other two examples are coming.